So, good afternoon everybody. Good afternoon. So, good to see you all again for the class. So, as a recap for today's class, last class we have been dealing with few theorems. So, we started with a theorem called superposition theorem. Hope you all remember superposition theorem. So, after superposition theorem, which gives the total response of individual responses based on individual responses, sum of all the individual responses, we completed few problems based on superposition theorem also. The next theorem what we are going to see is a very important concept as far as our circuits is concerned. So this has major applications in power system network also. So the theorem what we are going to see today is called as Thevenin's theorem. So this Thevenin's theorem gives the value of voltage and the resistance to be calculated, and we can convert any complex networks or any number of complex networks into a simple network consisting of a single voltage source in series with a single resistance. So that is going to be Thevenin's theorem. So what is this Thevenin's theorem? So a simple diagrammatic representation of Thevenin's theorem you can see. So this is a complex active linear network in series with a resistance RTH. Okay, so this can be redrawn also as an voltage source. This is taken as the VOC, or which is equal to VTH. That is Thevenin's voltage or open circuit voltage in series with a resistance which is called as RTH. So RTH is nothing but Thevenin's resistance. Okay. So the two terms associated over here is VOC, which is nothing but the open circuit voltage. So this open circuit voltage is also called as VTH, that is Thevenin's voltage. Where we found out the equivalent resistance without adding the load resistance, that resistance is taken as RTH, which is nothing but Thevenin's resistance. Okay, so based on this, I think you can understand what is Thevenin's theorem. So what is Thevenin's theorem? So across any pair of terminals A and B. So here if you take, this is A and B. Across any pair of terminals A and B, any complex network, okay, can be converted into a simple network consisting of a single voltage source VOC with a single series resistance RTH. So this is called the statement of Thevenin's theorem. So I'll just repeat what is Thevenin's theorem. So having a complex network can be converted into a simple network, okay, having one single voltage source which is called as VOC or VTH with the resistance RTH, in series with the resistance RTH. This is called Thevenin's theorem. So based on this Thevenin theorem, we will solve one problem so that you can understand what is the concept of Thevenin's theorem. Okay, so you just take out this problem as a case. Okay, so we need to find out what is the voltage across VAB. So we need to find out the value of voltage across VAB. So this is the question asked. So this circuit consists of an voltage source with some series parallel combination of resistance. So what is the procedure to be followed for Thevenin's theorem? We need to find out two values. One is, first we need to find out the value of RTH. So how to find out the value of RTH? We have some procedure to find out the value of RTH. So what is the procedure for? Yes, can anybody tell me what is the procedure? Yes. So series parallel combination of resistance. Before going for that, you need to remove the load resistance. If you have any load resistance, remove the load resistance. Remove load resistance. Second step is, if you have an voltage source, what you should do? Short circuit. So you have to short circuit the voltage source. If you have a current source, what you should do? Open circuit the current source. So after doing these three steps, you can go with the series parallel combination of resistance and find out the value of RTH. One step is over. What is the second step? The second step is to find out the value of VOC. So to find out the value of VOC, we have to remove the load resistance. Okay, that's all. So we have to remove load resistance and find out the current and then the voltage passing through the circuit. So these are the two steps to be followed for Thevenin's theorem. So with the same two steps, I am just going to implement this in this problem. So what are the two steps? First step, I need to find RTH. So how to find out RTH? This is this across A and B. This is already open circuited. So from this point, I need to find out the value of RTH. Okay. So for that case, I need to first. This is a voltage source. So what should I do with this voltage source? Short circuit the voltage. So we draw this diagram just by short circuiting this voltage source. So I just draw a straight line. 7 ohms, 6 ohms, 5 ohms. 5 ohms, 10 ohms. So 7, 6, 5, 10. So what's the first step? So since we need to find from this side across A and B, go with the series parallel. The opposite end, 7 ohm and 6 ohms are in parallel. So what is the formula? 1 by R equivalent is equal to 1 by 7 plus 1 by 6, or R equivalent is equal to 7 into 6 divided by 7 plus 6. What is the answer? 3.23 ohms. So just redraw this diagram. So we have one resistance in series with 5 ohms, again 5 ohms, 10 ohms. 3.23, this is 5 ohms, this is 5 ohms, 10 ohms across AB. Now, how this 3.23 and 5 ohms are connected? Series. So 3.23 series with 5 ohms. So what's the answer? 3.23 plus 5. What's the answer? 8.23 ohms. So I get an answer circuit diagram like 1, 2, 3. So this is 8.23, this is 5 ohms, this is 10 ohms. How this 8.23 and 5 ohms are connected? Parallel. So now go with 8.23 parallel to 5 ohms. What is the answer? R equivalent is equal to 8.23 multiplied by 5 divided by 8.23 plus 5. What's the answer? 3.11. Okay. So finally, last step is 3.11 ohms and 10 ohms. How they are connected? Series. So what's the answer? R equivalent is equal to, that is RTH is equal to 10 plus 3.11. 13.11 ohms. So answer is 13.11 ohms. So this is equal to RTH. We have finished the first step, that is RTH is equal to 13.11 ohms. Now go for finding out the second step, that is find out the value of VOC. So how to find the value of VOC? So remove the load resistance. We will take two loops. This is loop 1, this is loop 2. So this I take it as I1, this I take it as I2. Okay? So two loops, find step 2, find VTH. So from this, forming the loop equations, I can form directly two matrices consisting of I1, I2, which is equal to 2 vectors. Okay, so totally we need to find out I1 and I2. I2 is the current passing through this 5 ohms. So if I directly find out I2 also, that is enough. Okay, so what will be my expression? I1 is 7 plus 6, 30. So here it is going to be minus 25, and second side we don't have any source, so it is 0. So 7 plus 6 is minus 13 and plus 6. Next step. In loop 2, 6 plus 5 is 11, that is minus 11 and 6. Am I correct? 16. minus 16. Okay, so this is going to be the answer. So from this, to find out del minus 13, 6 minus 16, what's the answer? 175.
Do something.
172. So I'll find out the value of del 2 directly. So del 2, substitute this minus 25, 0, 6, 13, 6, and minus 25 and 0. What's the answer? 150. 150. So to find out I2, which is equal to del 2 by del, which is equal to 150 divided by 172. What is the answer? 0.872 amps. Now we have got the current passing through this 5 ohm resistor. So this answer is 0.872. We want the voltage across A and B. So what we should do? So VAB is equal to I2 into R, which is equal to 0.872 multiplied by 5. What's the answer? 4.36 volt. Okay, we got the final answer of VOC, which is equal to 4.36 ohms. Now my Thevenin equivalent circuit becomes single voltage source in series with a single resistance. So this VOC is equal to 4.36 volt and RTH is equal to 13.11 ohms. So this is our final Thevenin equivalent circuit. Hope you understand?
Yes, sir.
Thank you. We'll meet in the next class.